Good morning, class. We are looking at section 5.3, the fundamental theorem of calculus. There are many integration formulas we should be comfortable with. We've looked at the concept of areas and distances, okay? And there are various ways of calculation using the left endpoints, the right endpoints, the midpoints, and if we take a limit as n goes to infinity, it becomes the actual area under the curve. Then we looked at the definite integral, which is defined as the limit of the summation of f of x by delta x as n goes to infinity, where delta x is b minus a over n, and x sub I is a plus I delta x, which is in essence using r sub n. So that's by definition. And now what we want to do, we are going to go with the easy way out. Okay, so let's first look at what happens here. The fundamental theorem of calculus has two parts to it, class. In short, this is one. Okay, let me put numbers. The numbers don't really mean that much as far as I'm concerned, but I believe this is number one in your text and this is number two. In short, the integration of f of x dx from a to b, which is a definite integral, which is a number, can be calculated by finding any antiderivative and evaluate them at the end points, namely a and b. Number two says the derivative of the integral is the function itself. So the fundamental theorem of calculus is appropriately named because it establishes a connection between the two branches of calculus, differential calculus and integral calculus. It gives the precise inverse relationship between the derivative and the integral. So one more time, look at number one and look at number two. All right, here's the theorem. We're going to read it and we're going to try to prove that in a moment. So let f be a non-negative continuous function over the interval of 0 to b. Let a of x be the area between the graph of f and the x-axis over the interval of 0 to x, where x is between 0 and b. Then a of x is differentiable function, okay, where f a prime becomes lowercase f. To find the area under the graph, find any antiderivative of capital F, antiderivative capital F of f, lowercase f, evaluated at the end points and calculate f of b minus f of a. The result is the area under the graph over the interval. Then the definite integral of f from a to b is defined as such. As you can see, the idea is that this limit is the definition. This is the definition. Now we can prove it can be done this way, which makes life easier. That's the idea behind this. And so FTC1, okay, let me just do this. FTC1 is the first one, which says the definite integral of f of x dx from a to b is capital F of b minus f of a. And the second one, or FTC2, the derivative of the integral of a to x f of t dt equals f of x. I want to make sure everybody understands that we are taking the derivative with respect to x, and this is a dummy variable, must be the same as this one, and this is the final independent variable. Now the lowercase a is any number, okay? Now let's look at the proof of this theorem. So again, we are looking at a non-negative continuous function. We're looking at the positive function over the course of a to b, okay? A of x is the area between the graph and the x-axis, okay, from a to x, where x is between a and b. Then a of x, capital A of x, is a differentiable function of x, and a prime, capital A prime, is lower f of x. So that's what we are looking at as far as the theorem. We want to prove this. So how do we prove that? Let's first go with the differentiation of a of x by its definition, everybody remembers the limit, right? So this is x, by the way, and this is area of x. So anywhere you pick it up, that becomes the area of that point. Over here, if it's x plus h, that would be the area of x plus h. In other words, I hope you realize from a to x, that would be the area of x. If I were to, this would be area of x, okay, class? Whereas area of x plus h would be the blue one, meaning, let me use a different color, meaning this one. This would be the area of x plus h, okay? We have that, okay? That's if a of x, capital A of x represents the area. Now, look at this green shaded region. We are going to look at in a moment. Stick with the green shaded region. Number one, as far as the differentiation is concerned, this is the definition class. A prime of x is the limit of a of x plus h minus a of x over h as h approaches 0. This is by definition of differentiation on the one hand. On the other hand, if you look at the green dashed region, what do we have? We almost have a rectangle. So take a look at how we calculate the area of that rectangular piece, okay? So a of x plus h minus a of x, that would be the green shaded region, okay? Just based on how we have defined a of x. But that rectangular piece has the width, okay, times the height, where the width, I hope you realize, class, this width from here to here is h. So h times the height. H times the height. Now, what is the height? Roughly f of x. But understand, f of x is not the same as f of x plus h. So this is a rough estimate. We take one of the endpoints, it doesn't matter. So what we are saying is that this is an approximation of that. Obviously, this approximation gets better as h becomes what? Smaller and smaller, right? So let's take a limit and let h go to 0. So we are going to take a limit of f of x equals a sub x plus h minus a sub a of x over h as h approaches 0. So take a look at this one. Again, we are dealing with this, and we know this is an approximation, and we can take a limit. And remember, when h goes to 0, becomes identical. This is important to see. Let me just put a different color up here. And so this one, class, is an approximation, and when h goes to 0, becomes exact. On the one hand, we have this. On the other hand, a prime by definition is this limit. Look at the right side. Because the right side happen to be identical, the left side must be the same. Now, what is the right side of this equation is a prime. What is the left side? The limit of f of x as h approaches 0 is f of x. And so we proved capital A prime is lowercase f of x, which is the proof of FTC 1. FTC 1 class. This is the proof of that. All right, let's use it now. As of this section, not the previous section, we can use the easy way out. So let's do that. We want to integrate this. So we just write 1 over 8x to the power of 8. And we don't write the constant because the constant will go away and it has no bearing. Okay. You plug in 1 and you plug in 0. 0 makes it 0. So just 1 makes it 1 over 8 and you're done. So take a look at this tip. I can't emphasize this enough. There is no need for a constant because it will go away, class. All right. I hope you remember this is the same as 1 over x, therefore is a natural log. So the answer is ln2 minus ln1, and I hope you remember that ln1 is 0. This one is 0, class. Okay. Now, if we didn't put an absolute value, it's fine because the limits a and b are both positive. However, take a look at this example. We must put an absolute value because the limits are no longer positive. And so what happens here? You get ln of the top minus ln of the bottom. And if you didn't have an absolute value, it wouldn't work. Ln of -1, that means ln1, which is 0, minus ln of absolute value of -2 is ln of 2, so minus ln2. All right. The integral of 0 to pi sine x dx. Okay. If you recall, the derivative of sine is cosine. The integral of that is negative cosine. So minus cosine pi minus cosine 0. And I hope you remember that cosine pi is -1, cosine 0 is +1. So you have minus -1, and then minus -1, and they add up to 2. Okay, they add up to 2. And pay attention to the tip. I can't emphasize this enough, class. Okay. Simple case. Let's integrate 5/3 x cubed. Again, by now, I'm hoping everybody's comfortable with that. 5/3 x cubed minus 2x squared plus 2x. We don't need the constant. We evaluate it from 0 to 2, which means we plug in 2. We evaluate it. We plug in 0. By the way, when you plug in 0, you get 0, class. So let's plug in. I'm hoping everybody is okay with that. I don't want to waste too much time on that. This is 8, class, okay? This is 4, and this is plus 4. And when you add them up, you end up 28 with 28/3, okay? So that's very straightforward. 28/3. Again, as we did with differentiation, we have a rational expression. We can simplify or divide. This is one piece, giving us 4v cubed. This is the second one, minus 3. So that's the first step. And now it's simple. 4v cubed gives us v to the power of 4, minus 3 gives us minus 3v, and evaluation from 1 to 2, class, that becomes a simple algebra. I hope everybody is comfortable with that. So plug in 2, plug in 1. When we plug in 2, we get 2 to the power of 4 minus 3 times 2, and when we plug in 1, basically 1 minus 3. So this is obviously 16 minus 6. So this is 1 minus 3. So plus 2. Okay. There you have it. Simple. I hope everybody is comfortable with this. We did this before. We didn't evaluate it from 2. I hope you remember that. We cut it into 3 pieces. And the first one is simply x. The second one is a natural log, minus 7 natural log of x. And the last one becomes minus 2 over x. This is in your notes, but quickly This is 2x to the power of minus 2. And so 2 over negative 2 plus 1, x to the power of negative 2 plus 1, which results in minus 2 over x. And let's plug in. Okay. So basically what happens is that this goes to 0, right? Because ln 1 is 0. So 1 minus 2, this is negative 1. Okay. So this whole thing just add 1, which means you're adding 3 and 1, 4 minus 2/3, which gives you 10/3. Now, this is an exact answer. You don't need to change that class, okay? So 3 plus 1 is 4, minus 2/3 is 10/3. What about minus 7 ln 3? You keep it intact, okay? Good. Simple, straightforward, I hope. Again, we've done part A, okay? So we know the answer is t plus sine t. This has been done. Now we are adding these limits of 0 and pi over 2. So if you plug in pi over 2, you get pi over 2 plus sine pi over 2 minus, when you plug in 0, t becomes 0, sine of 0 becomes 0. So this is your answer, and sine of pi over 2 is 1. Okay. Let's look at the next one, and we are going to replace the square root of x with x to the power of 1/2. We replace the x with square root of x with x to the power of 1/2, and this is what we get. Now, 5 divided by 3/2 plus 1, x to the power of 3/2 plus 1. Same thing here, 3 divided by 1/2 plus 1, x to the power of 1/2 plus 1. You don't need the constant because you are evaluating everybody. So 1 plus 3/2 is 5/2. 5 over 5/2 is simply 2. This one is 3/2. This one is 2. So that's what we have. 2x to the power of 5/2 plus 2x to the power of 3/2. We evaluated from 1 to 4. So plug in 4, plug in 1. First, this one is 2 plus 2 or 4, okay, class? So minus 4, that part, because 1 to any power. But just a quick work on this one. 4 to the power of 5/2 is square root of 4 to the power of 5, which means 2 to the power of 5, which means 32 times 2 makes it 64. 4 to the power of 3/2 is square root of 4 cubed, 2 cubed, 8, 2 times that makes it 16. Minus 2 plus 2 is 4, and you get 76. Simple calculation, you can do it on your own. I wouldn't worry about that. I hope you realize the only calculus that we had was this one with the asterisk. Everything else is algebra class. Everything else. So you can't afford to be uncomfortable with those parts. Here's another example. We want to evaluate this integral. And by the way, if you look at the explanation here, if you have this one if you have this one, really makes no difference, just in case. If you have this one as the domain or this one, makes no difference. I want you to know that. Because we are interested in the integral of the function from -2 to 2. So even if it were defined that way, that would be okay. So it's a piecewise defined function. We have two different pieces. So from -2 to 0, we use the top one. From 0 to 2, we use the bottom function. So that's the really only thing that distinguishes this question from other questions, and that is a piecewise defined function. Now, I don't think anybody has any problem evaluating this. I hope you don't. So the first one becomes 2x, evaluated from -2 to 0. The second one becomes 4x minus 1/3 x cubed. Now, I'm going to assume you can easily do that, so I'm not going to spend too much time on that. Just plug in 0, plug in -2, the other one 2 and 0, and this is what you get. Of course, just quickly, this goes to 0. You don't have to worry about that. The rest is easy calculation. Again, this goes to 0. Okay. So this is 4. This is 8. This is minus 8/3 because this is 8. And so you have 4 and 8 is 12 minus 8/3 is 28/3. So I hope everybody is comfortable with the basic algebra behind this, okay? So that shouldn't be too big of a deal. So algebraic steps sometimes take longer, but I have to assume you're comfortable with that. You can't afford to mess that up. Okay. The integral of -1 to 2, 4 over x cubed dx is equal to this and is equal to 3/2. And that's not a true statement. Can anybody tell me what's wrong with this statement? There is something wrong. Anybody notices what's wrong with this statement? Why it doesn't work that way? Well, the function is not continuous. Okay, from negative to positive infinity, specifically from -1 to 2. What matters is this. When you look at this function, it's continuous everywhere except at 0. So if the limits do not contain 0, that's fine. If you go from, let's say, I don't know, -5 to -1 or 1 to 7. As long as 0 is not there, we're fine. We can calculate it. But remember, it has to be a continuous function. So I thought it's worth looking at. All right. Here's another example. And again, this is in essence, the FTC second one can be proved that way also, this way also. So we are looking at the derivative of the integral of a to g of x f of t dt. As you recall, we mentioned the derivative of a to x f of t dt is f of x. And this, by the way, you can use this one to prove that. We are going to use this one actually to prove this one, okay? So first, let's ignore the dx and let's, integrate this part, okay? So it's, if the antiderivative of lowercase f is capital F of t, then you plug in, okay? So this one gives you capital F of t, so you evaluate it. So we want this part, capital F of t dt. So let me just actually write the step that maybe. So it becomes capital F of t going from a to g of x, everybody. So capital F of g of x minus capital F of a. Now we are going to differentiate this. That means differentiation of this statement. And I hope you realize when you differentiate class, this one, you use the chain rule. So it becomes what? Capital F prime of g of x times g prime of x. Capital F prime or lowercase f. Remember, let me just write that up here again, class. Capital F prime is lowercase f. And so what about f of a? We may not know what's f of a. We just know it's a constant. It's a number class. The derivative of that is 0. And we are done. So what does it mean? By the chain rule class, if you're differentiating, see, look at this one. If we are differentiating this piece, we just get f of x. But instead of x, if we have a different function, this function sits in there, and then tag along g prime by the chain rule. Tag along g prime by the chain. Of course, the assumption is, of course, continuity. So here's an example. We want to find the derivative of this function, okay, by ftc. And of course, this is a continuous function. I hope you know that, because the square root of 1 plus t squared, okay. The domain is all real numbers. It's a square root. 1 plus t squared larger than or equal to 0. It's always the case. Because this is x, simply put, if you call this one f of t, this is your f of t, everybody. Let me just write it. Okay, just it is f of t. Okay, so therefore, you replace it with x. So f of t is the square root of 1 plus t squared, is a continuous function. Why? I have explained it to you. It's a square root function where 1 plus t squared must be larger than or equal to 0. It is always the case, okay? Square root, okay, square root function. Okay, remember the domain, how do you find it? You set 1 plus t squared, and it's all real numbers. Okay, so everything works. And therefore, the derivative of that is simply square root of 1 plus x squared by ftc. What if we have a case like this? Well, we are going to use this one. So we are going to replace the variable t with whatever we have here. So t is replaced with x squared. We get sine x squared. And then g prime of x. Remember, this is g of x class. Okay. So f of g of x makes it sine of x squared, and then times the derivative of this guy, which is 2x. Okay. So I want to make sure if we want to sort of explain that, we say, okay, f of t sine t, g of x equals x squared. Okay, so we get f of g of x times g prime of x, and we put the 2x in front. That's really the idea. Okay. You could also do this, class. Take a look. You could integrate this, becomes negative cosine t, evaluate it from 1 to x squared, and then differentiate. I highly recommend you try this. So one more time. When you integrate sine t, you get minus cosine t. Evaluate it from 1 to x squared, and then differentiate it, it gives you the same answer. Try that one, class. All right. And this is question 78. How about this one? If we want to differentiate now where the bottom and the top are both functions instead of the bottom being a number. Well, we already remember how it's done when it's a number. Okay, so we are going to use that, everybody. We are going to use that and expand it. How about that? We are going to use that and expand it, which means we are simply going to rewrite this as follows. Okay. I hope everybody understands what we are trying to do. We are trying to use the previous theorem. Okay. So g of x to a plus a to h of x. And the first one, remember how it was. The bottom was a number, it doesn't matter what, and the top was a function. So this is good, but this is not. So you flip this over and you create a negative sign. So take a look. If I interchange a and g of x, and I can, then I have to give it a negative sign. Okay, I have to give it a negative sign. I hope everybody is following that. And so what happens next, now we apply the theorem that we know. Okay, class? We apply the theorem that we already know. Negative sign remains. Now f of g of x times g prime of x plus, now f of h of x times h prime of x, you put this one second, and this is your final answer. What does it mean? Let's just quickly recap. It makes it nice and easy if we understand from the get-go. Look at the top one. What this says, plug in h of x and then times h prime of x minus plug in the bottom one times g prime of x. Very straightforward, class. Okay, very straightforward. I hope everybody is okay with that. Let's look at some examples for that. All right, let's first start with what we did before, the original one, when we looked at, okay? So the derivative, when we are going from a number, a constant, such as a or 1, doesn't matter, any number, pick any number, doesn't matter. And the top is a function, you just put the function in. So in this case, tan t, so I'm going to put the function in, becomes tan of x squared plus x, that's f of g of x, times g prime of x, times the derivative of x squared plus x, which is what? 2x plus 1, and I'm going to put it in front. I hope you see it's very straightforward, class. One more time, plug in x squared plus x, and then times the derivative of that. So that's the first one we used. Okay, class? That's the first one we used. Right? Very simple. Now, let's look at another example. Now what's going on? Well, here's the second one we use. Look at the bottom. If we have two functions, the bottom is a function and the top is a function, okay? So here's f of t. So f of t is t squared. Replace the t, everybody, with the top. So you get sine x to the second power, or sine squared x. And then times the derivative of that. The derivative of sine is cosine x. Minus, now let's plug in tan. So we get minus tan x to the second power, or tan squared. And then times g prime, times the derivative of tan, which is secant squared. So one more time. Plug in sine, and then times the derivative of sine. Minus, plug in tangent, and then times the derivative of tangent, which is secant squared. So we just are following this formula, class. We are just following this one. One more example. What if the bottom is a function and the top is a number? Remember when we went over the proof of that, we just flip them over and we give them a negative sign. So again, it's the same thing, but pay attention to this negative sign because we are interchanging the lower and upper limits. 1, which was the upper limit, now is the lower limit. So therefore, we can use this one, everybody. So plug in sine. So you get square root of 1 plus sine squared times the derivative of sine, which is cosine. Don't forget there's a negative sign in front. And this is it.